Hi everyone, I'm Antonia Praetorius from the University of Amsterdam, and today I will give you a short lecture on exposure modeling of chemicals in the environment. Models play actually a very important role in chemical exposure and risk assessment because they can help us understand how measured data on chemical concentrations in the environment can be related back on one hand to specific emission patterns of chemicals, but also to their fundamental physicochemical properties, like for example their partition coefficients or degradation half-lives that you have already heard about in previous lectures. And models can of course also be used to predict exposure levels of chemicals under future scenarios. So for example, in the context of assessing the impacts of climate change of chemical exposure, but also for example to assess the impact of different possible regulatory measures on chemical concentrations in the environment. And finally, they're of course also very useful to estimate chemical exposure levels for chemicals for which we currently have no exposure data available, for example, due to limitations in analytical techniques, or also for locations for which no sampling campaigns had been performed. In this context, environmental fate, or also called exposure models, they really serve as an important bridge between these different elements. In a model, we can combine data on chemical properties and on emissions together with information on the characteristics of the environment of interest into a mechanistic description of fate processes like transformation processes and transport processes that influence the likely behavior of chemicals in a given environmental system. And then after solving such a model, we can get different types of model results. Typically, these will be concentrations of chemicals in the environment, also called exposure levels. But we can also get as model outputs, for example, mass fluxes of chemicals between different environmental compartments, or estimations of their likely overall persistence in a given environmental system, or their potential to undergo, for example, long-range environmental transport. Ideally, when possible, we like to compare our model estimates to field data so that we can evaluate the model performance and, if necessary, go back and improve and refine the model. But this is not always possible because there are, of course, a lot of limitations also in the availability of monitoring data. And we can also not do that when we use the model to predict future scenarios. Commonly predicted environmental concentrations, they are also called PECs, compared to measured or predicted toxicity thresholds, also called PNECs, predicted no effect concentrations. And this is very important in the context of chemical risk assessment, and it's something you will hear more about in the risk assessment lecture. So for now, let's have a closer look at how we actually build these kind of models. So from the chemical side, the key inputs into environmental fate models are partition coefficients. So for example, the octanol water partition coefficient, KOW, or the Henry's law constant, or air-water partition coefficient. These give a measure of the affinity of a chemical for different environmental compartments. And the second type of inputs on the chemicals are the degradation rate constants or half-lives in different environmental compartments. And together with emissions, so information on chemical emission, locations, and amounts, as well as information on transport processes across different compartments, for example, transport via wind or water flow, or through sedimentation. These four elements constitute the main building blocks of most environmental fate models for organic chemicals. Most models that we use in chemical exposure assessment, they are based on the so-called multimedia mass balance modeling approach. In that approach, we represent environmental media as discrete, well-mixed boxes, such as the one that you can see here in the left lower side of the slide. And in these, for each of these of the boxes that we have in our model, we then set up a mass balance equation. So an equation that tracks the change of mass or of concentration of our chemical of interest over time in our environment as a function of all input processes and all output processes that add or remove chemical from a given compartment of interest. So this can be, for example, in terms of inputs, this can be external emissions into our model system, but also transfer of a chemical from a neighboring box in the model into the model the box described by the given equation. And in terms of outputs, this relates on one hand to transport, again, out of the box of interest, but also importantly to degradation of the chemical within a given environmental compartment, which then removes the chemical completely out of the system. Here the partition coefficients are very important because they on one hand drive the diffusive transport across different environmental compartments, but also indicate which proportion of a chemical is free versus sorbed to solid phases in our environment. So, for example, a chemical that is sorbed to a sediment particle or an aerosol particle in the air will then also be transported via this solid particle and hence be transported differently than if it was freely present in the environment. So these are our, let's say, underlying building blocks to represent a more complex environment. We normally connect several such well-mixed boxes where each box represents a distinct compartment. And compartments that are often represented in such multimedia environments are, for example, air, soil, water, sediment, or biota. But it's also possible to include additional compartments like, for example, vegetation or different types of subcompartments. So we can have, for example, agricultural and urban soils or marine waters and also fresh waters. And then once we decide on which kind of compartments we want to have in our model, we then set up one mass balance equation for each of the boxes in our model. Mass balance like the one that I introduced on the previous slide. And then these we end up with one equation for each of the boxes, so each compartment in our model. And this results in a system of coupled mass balance equations that can then be solved either as a function of time or at steady state to then obtain the concentration of a chemical of interest in each environmental compartment as a function of time or at steady state. So yeah, this is basically how the underlying framework typically looks. The model that is shown here on the slide is called unit world model, which represents basically the world as a very generic, simplified environment with average conditions for the different compartments. These are normally used as so-called evaluative models, so they're not used to predict exact concentrations of a chemical in a specific location, but more as a reference point to compare how different types of chemicals would behave in a typical environment. So, for example, to compare how likely it is that chemicals accumulate in certain environmental compartments, or to compare different chemicals for their with respect to their overall persistence in a typical environmental system. We can also achieve a higher spatial resolution, for example, at the regional scale or even at the global scale, by connecting just a larger number of these boxes in our model, where all these boxes follow the same underlying mass balance modeling approach. but by connecting more of these boxes, we can increase our model complexity and our spatial resolution. So, for example, by connecting multiple water sediment boxes, we can represent a 2- or 3-dimensional river or watershed, and we can even connect a large number of multimedia boxes or model units into a global scale model that can really be used also to represent chemical fate at a very large scale. Then, depending on how many boxes we connect and how big these boxes are, we can achieve different levels of spatial resolution. The smaller the boxes, the higher the spatial resolution, but also the more equations we need to solve when we run the model. So higher spatial resolution also comes hand in hand with higher computational demand and also with increased data needs for parameterization. So it has to be balanced carefully on what spatial resolution is really necessary and desired for a given question, and also with respect to the data that are available for parameterizing our models. So now I will briefly show you some examples of such environmental fate models. So here, for example, is a spatially and temporally resolved watershed model for the Danube River. It's also based on a multimedia mass balance modeling approach, and it's using the outputs of a hydrological model to better parameterize the individual boxes or individual compartments in this multimedia box model. And you can see here in this graph how the model results for different scenarios based on different assumptions agree overall quite well with monitoring data here on the example of PFAS in the PFOS in the Danube River. An example of a global scale model is this one here, the Beta Global model, which is able to estimate the distribution of chemicals as a function of different environmental and also climatic differences. So this is also a very nice, very interesting model to use. You can actually access it freely and play around with also yourself if you're interested. Same for the next model that I'm going to show you, the Simple Box model. You can also download that and use it for your own chemicals or case studies of interest. This model is a model that is also used a lot in the regulatory context. It was developed by the Dutch RIVM and is used, for example, in the context of REACH. And this model is again a more or less resolved model on the spatial level. It's a unit world type model, but it's set up to evaluate the fate of chemicals at different scales, at the regional, continental, and also at the global scale. All the models and also the theory that I've discussed so far are applicable to organic contaminants, but we also have different types of contaminants, like for example nanomaterials and micro and nanoplastics, which are particulate contaminants. And these can also be modeled with multimedia mass balance models, but adjustments have to be made to the way that the processes in these models are represented. So for example, instead of using partition coefficients, these models include descriptions of aggregation processes and fragmentation processes of these particles. There's quite a lot of development in this field, and on this slide you can see some examples. For example, the first two that are based also on the Simple Box model that I showed in the previous slide. So to summarize, environmental fate models play a very important role in environmental chemistry and also in the regulatory context. They allow us to integrate the understanding that we have on chemical fate and data that we have on their fundamental properties to estimate exposure concentrations in different scenarios, in different locations, and at different spatial scales. which is very important to increase our understanding of chemical fate and exposure, but also to support regulatory activities. There are many more models, of course, than the ones that I've presented today. There are also models that are more specific for chemical transfer, for example, in food webs and biota, or models that focus specifically on human exposure, but that are oftentimes also based on similar principles as what I've presented today. And finally, please keep in mind always that no model is going to be a perfect representation of reality. All the models that we are using are strongly simplified versions of the environment and also of the behavior of the chemical in these environments. So when you interpret model results, you have to be very aware of those simplifications and also of how they would affect the outcomes of the models and also the associated uncertainties. With that, I thank you very much, and I invite you to look at some of these models. They are linked also on the course website, and play around with them a little bit, for example, for your own case studies or projects. Thank you very much.